Okay, let's talk about curvilinear coordinate systems. So normally, you have your x and your y. Oops, usually it's the other way. Your x and your y and your z like that, okay? And if you've got a vector out in some space, sometimes it helps to do that coordinate system. Sometimes, if you want to do an integral, sometimes it's easier if you have like a sphere, for example, to use a different coordinate system where you talk about the position of a imagine you want to talk about this point right there, okay? That point right here. Let's change the color. Okay, that's the point you want to describe. Well, you could define it as an x coordinate and a y coordinate, okay? And then if it's out in space, you could define it as a z coordinate. Or it could be simpler to define it as a r, this distance here, r, and then a theta, that angle there. And between those two coordinates, since r is constant, in this case it's 2 dimensions, theta is any point along that line since r is fixed, okay? So sometimes you want to go to that coordinate system, r and theta, and then if this is out in space, if that vector is in 3 dimensions, and you have another x direction there, then you can do r theta for this angle, and then for that angle in the xy plane, that is phi, for example, or phi, however you want to say it, okay? Always say it differently than everyone else, so if someone says phi, you should say phi, just to assert dominance. Okay, so there's a couple different coordinate systems. One is the spherical coordinate system, where your x coordinate is r sine theta times cosine of phi. So those are your two angles, your r, your theta, and then if this vector is out in some space there, then there's your phi there. So this vector, or this angle here, is in this plane, the YZ plane, let's say, and then phi here is in the XY plane. So I'm doing a bad job drawing it, but let's take a look if they're down here. Yeah. So there's your phi angle in the XY plane, and there's your theta in the YZ plane. Okay, and then that point then is totally parametrized by r, theta, and phi, just like it is parametrized by x, y, and z. Okay, and then how you bounce between x, y, and z is r sine theta cosine phi, or r sine theta sine phi, or r cosine theta for the different coordinates. And you can easily see that if that's your vector and you want the component of it down there in the x and y coordinates, you use your theta and your sines to pick off the sides of that are along your x coordinate system. Okay, that's my pencil. I don't know why it's not. Okay, there we go. So if you double tap with your finger on it, it switches between eraser and pencil. You can see it. Sometimes it's not working. I dropped it too many times, I think. Okay, so anyway, so you can use r, theta, and phi. You can go from r, theta, and phi to x, y, and z, and that's how you do that. Or you can go to r, theta, and phi in the other direction. So to get your r, theta, and phi, then you do this. Okay, so you're going the opposite direction now. So that's how you can define a vector, any vector. You just have an r, theta, and phi unit vector, just like you'd have an x, y, and z unit vector, and then an amount in the r direction, theta direction, and phi direction. And you can bounce between r, theta, and phi and x, y, and z using these transformations. Okay, so that's all those are. Blah, blah, blah. So we're going through this. Yeah, and he's just talking about the infinitesimal line elements now. Your dr vector would be along your r, so if you wanted to change your r vector a little bit that way, r times d theta, remember arc length is r times the angle, and that'll tell you the length here. So r times this little d theta will give you that amount there. And then r sine theta d phi, again, the amount in the phi direction is pointing that way. So those are your infinitesimal line elements, just like you have line elements in regular, dl might be dx plus dy plus dz and so on. So here you can bounce between the element in the theta direction, the element in the phi direction, and so your total line element then is a little bit of change in the r hat direction, a little bit of change in the theta hat direction, and a little bit of change in the phi hat direction. So this is simply, if you change the r unit vector a little bit, it just gets longer or shorter, but it's in the same direction as r. Your theta unit vector is of the amount r d theta, and so there's your amount in the theta hat direction, and the amount this way is r d theta, or d phi in this case, but you need the sine theta component of it, and then, so that's this side of it, and then you're moving it an arc length d phi, and so that's where that comes from. Okay, so those are just arc lengths of your tiny change. And then we have our volume element, which is the multiplication of these things, just like dx times dy is area, and then times dz is volume. You have the same thing. So your volume element is r squared sine theta dr d theta d phi, and we're just multiplying dr times r d theta times r sine theta d phi, and that's where you get this thing. Okay, and again, that's a volume from these directions up here. Okay. Blah blah blah. Yeah, and then there's your area. Same thing. It's just dl phi dl theta in the r hat direction, because that's your this surface element basically. Okay. Blah blah blah. And there you go. There's an example of a couple patches of your area. So if you want to find the volume of a sphere, you integrate over your volume element. Okay, integral over d tau. So you're finding the volume of a sphere. You're integrating from the center of the sphere out to the radius, so 0 to r, and then you're going around the sphere, 0 to pi, and then you're going, well, actually going from up to down to the equator, sweeping through the circle from 0 to pi, and then so you're sweeping down that way, and then you're sweeping all the way around. So that's how you get your area. So you're integrating from there along this line to get this slice, and then you're integrating all the way around to get the full volume of the sphere. So 0 to r from the center out, 0 to pi from there down to there, and then 0 to 2 pi there all the way around. Okay, and so if you just do that, and then your volume element is the multiplication of length times width times height, then you get, 4/3 pi r cubed. Haha, that's the volume of the sphere. So if you ever forget the volume of a sphere, you can reintegrate it from scratch and then look really cool, or look like a jerk. It depends on, when you pull that out to do it. Okay, so, and then we have the same thing with our gradient divergence curl in our special unit vectors, and then the Laplacian comes in as this thing looks really nasty, and that just comes from, you are using the gradient, you take these transformations, and then you end up taking dx, dy, dz, and so on, but you're taking it with respect to all your angles. So dt dx becomes dt dr dr dx, okay? And so then you have to do blah, 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 all those things. When you do that, when you carry that integral, or those derivatives out, you end up getting this, then the divergence is that, the curl is this, and your Laplacian is that, and you're going to have to do that, find these formulas by just doing the derivatives. Everybody has to do that once in their life, so I'm sorry, but you just have to do it. I had to do it, and now you have to do it. That is the way of things. Okay, 1.42, we're getting into cylindrical coordinates. This is a different thing where your point, this would be, you would use in the case of a cylinder, because the outer edge of it does not curve back into the z-axis, so that element is constant. The distance from the z-axis is constant. So we call that s. And then phi is the angle around. And then as you move up and down z, your distance from it stays the same, so we just keep that as s. And there's your angles. You can see that's just a regular transformation, cosine plus sine, and then minus sine plus cosine, and so on. So our little displacements then, you change s a little bit, it just changes s a little bit. You just move a little bit that way. dl d phi, you just move a little bit that way, and it's the same thing. S, this length times the angle gives you that arc length. Yeah, so that's your element there, and then you just move a little bit in the z direction when you want to move in the z direction. So now your total infinitesimal element is a little bit in the s direction, a little bit in the phi direction, and a little bit in the z direction. And then your volume element, you multiply the three of those things together, and then you get your gradient, divergence, curl, same thing, and your Laplacian. You're going to find these things once in your life and never do it again, but you're going to know where they came from, and then you're going to have to just look in your book if you ever need to find something. Because sometimes, believe it or not, it is actually easier to use this formula than try to do an integral in x, y, z over for a cylinder or a sphere. So, but we don't spend a lot of time after we do this doing that type of thing. Okay, so that's 1.4. Bye.